Imagine a world without predictability, a world where patterns are invisible and problems have no general solutions. This was, in many ways, the world before algebra. But what exactly is this mysterious branch of mathematics, and how did it come to shape our modern world, from the bridges we cross to the phones in our pockets? At its heart, algebra is the language of unknowns. It's about taking specific arithmetic problems and generalizing them, using symbols to represent numbers and quantities. This simple yet profound idea allows us to solve a vast array of problems that would otherwise be intractable. Our journey begins not with a European scholar, but in the cradle of civilization, ancient Mesopotamia. The Babylonians, over 4,000 years ago, were using sophisticated methods to solve problems that we would recognize as quadratic equations. They weren't using x and y, but their techniques were strikingly similar. Imagine a scribe trying to figure out how many bricks are needed for a rectangular wall of a certain area, with one side being a specific length more than the other. This isn't just arithmetic, it's a Proto-Algebraic problem, tackled with ingenuity on clay tablets. Move forward to ancient Egypt, and we find similar practical applications. The Rhind Papyrus, dating back to around 1650 BCE, contains problems involving aha or heap, their term for an unknown quantity. While not symbolic algebra as we know it, it showed a systematic approach to finding unknowns. The Greeks, while masters of geometry, often approached algebraic problems geometrically. Diophantus of Alexandria, in his work Arithmetica around 250 CE, introduced a more symbolic approach, though it was still a far cry from modern notation. He's often called the father of algebra. But the true explosion of algebraic thought, and the origin of the word itself, comes from the Islamic Golden Age. Around 820 CE in Baghdad, a Persian mathematician named Muhammad ibn Musa Al-Khwarizmi penned a groundbreaking treatise. His book, Kitab al-Mukhtasar fa Hisab al-Jabr wal-Muqabala, translates to the compendious book on calculation by completion and balancing. The word Al-Jabr literally means reunion of broken parts, or restoring balance to an equation by moving terms. Al-Khwarizmi systematically solved linear and quadratic equations, not with symbols, but with words and geometric proofs. His work was pivotal, laying the foundation for modern algebraic manipulation and problem-solving. The concepts developed by Al-Khwarizmi and other Islamic scholars traveled to Europe, largely through Spain. The translation of these Arabic texts into Latin proved to be a watershed moment for Western mathematics. By the 13th century, Fibonacci, known for his sequence, also introduced Arabic numerals and algebraic ideas to Europe through his Liber Abaci, literally Book of Calculation. This was a massive leap from the cumbersome Roman numerals. The Renaissance brought another wave of advancements. Italian mathematicians like Scipione del Ferro and Niccolò Fontana Tartaglia famously solved the cubic equation in the 16th century, though their methods were shrouded in secrecy and rivalry. Girolamo Cardano, Tartaglia's rival, eventually published the general solution to the cubic and quartic equations in his seminal work Ars Magna in 1545. This marked a profound shift, demonstrating that equations beyond the quadratic could be systematically tackled. Yet these solutions were often incredibly complex, making them hard to apply. What was needed was a clearer, more universal language. This is where symbolic notation truly began to flourish. François Viète, a French lawyer and mathematician in the late 16th century, made a monumental step by consistently using letters to represent unknown quantities and known parameters. This was a game-changer. Suddenly, an equation like 3x plus 5r 14 could be written and understood across different contexts, independent of the specific numbers involved. It allowed mathematicians to analyze the structure of problems, not just individual instances. René Descartes, in the 17th century, further solidified modern notation by using x, y, and z for unknowns, and a, b, c for knowns. He also famously linked algebra with geometry, creating what we now call analytic geometry. This fusion allowed geometric problems to be solved algebraically and algebraic problems to be visualized geometrically. It was a revolutionary insight that paved the way for calculus and modern physics. The 18th and 19th centuries saw algebra mature into a sophisticated field. Leonhard Euler contributed immensely, standardizing much of the notation we still use today, including the use of e for the base of natural logarithms and I for the imaginary unit. But perhaps one of the most profound developments was the realization that there wasn't just one type of algebra. Mathematicians began to explore different algebraic structures. Évariste Galois, in the early 19th century, despite his tragically short life, laid the groundwork for group theory. He showed how the symmetries of polynomial equations relate to their solvability, forever changing the landscape of algebra. This abstract algebra, as it came to be known, wasn't just about solving equations. It was about understanding the fundamental rules and structures that govern mathematical operations themselves. It's the algebra of algebras. George Boole, in the mid-19th century, introduced Boolean algebra, which deals with true-false values and logical operations like AND, OR, NOT. At the time, it seemed like a niche mathematical curiosity. Little did he know, Boolean algebra would become the foundational language of digital computing. Every circuit, every line of code, every operation performed by your computer relies on the principles he laid down. From the ancient world's practical problems to abstract group theory, algebra evolved from a set of specific techniques into a vast, interconnected web of mathematical ideas. So, where do we see algebra today? Everywhere. From the GPS in your car, which uses algebraic equations to pinpoint your location based on satellite signals, to the encryption that keeps your online banking secure, utilizing complex algebraic structures like prime numbers and modular arithmetic. Algebra is the backbone of engineering, allowing architects and builders to calculate stresses, forces, and material requirements to construct safe and stable structures. In medicine, algebraic models are used to understand disease spread, design drug dosages, and analyze medical imaging data. It's literally saving lives. And in the cutting edge of artificial intelligence and machine learning, linear algebra forms the fundamental basis. It's how computers process and understand vast data sets, recognizing patterns and making predictions. Every time you interact with an AI, whether it's a recommendation engine or a self-driving car, you're experiencing the power of algebra at work, crunching numbers in multidimensional spaces. From the humble clay tablets of Babylon to the complex algorithms of modern AI, algebra has been an indispensable tool for humanity's progress. It's more than just manipulating X's and I's. It's a way of thinking, a method of systematizing thought, and a language for describing the universe's inherent patterns. So the next time you marvel at a towering bridge, browse the internet, or witness the wonders of artificial intelligence, remember the unsung story of algebra. It's a story of human ingenuity, spanning millennia and cultures, continuously evolving to solve the problems of yesterday, today, and tomorrow. It truly is the fundamental language of our universe.